Good morning. Today's Tuesday, April 28th. Um, so we're going to start doing series parallel electric circuits. So before we were doing just a series circuit or just a parallel circuit. Now we're doing combinations of the two. Um, I'm going to split up this classwork into two sections. We'll do 1 and 2 today, and then we'll do 3 next class. So kind of making these a little bit shorter so they can sink in a little bit better. So work on this classwork, and as I go through it, you can also work on the homework and get those two turned in. I am going to post a review for the test pretty soon. Um, and then the test will be out next week, probably early next week. I'll probably put out the review later this week and the test at the beginning of next week, and we'll kind of go through that. And then after that, mostly just I'm probably just going to do a little bit of magnetism concepts, just because I like magnets and I have some things I built for them, and that'll be mostly it. MST, you're not having a final exam, dual credit. I still am not sure what's happening with your final exam. That is more out of my control. I'm going to see what I can do about exams and if I have to give you one. But there is a chance dual credit you might have to still take a final exam to satisfy Richland. Yeah, that's out of my control. I really need to figure out what Richland College is making me do for final exams. If there's a chance not to do final exams, I would rather not, because that's a lot of work. Um, Possibly, I might be able to use that because they are returning the AP test to us, so I might be able to use that as a final exam. We'll see. I'm going to try to not have a final exam if possible, and whenever I figure out more about that, I'll definitely tell you. All right, so getting into this, if you still haven't finished your series, like your simple series, simple parallel classwork and homework, do those, get those in so I can grade them. I try to make these where they parallel a lot, so hopefully these are going a little bit easier where your classwork and homework look very similar. So here we have a 6-volt battery connected directly to a light bulb. A lot of times you'll see a light bulb is a circle with an X in it. That's just a symbol that's used a lot. So we have a 20 ohm light bulb that's in series with the battery. But then after going in series, we get to this point where we have two 10 ohm resistors in parallel going to the battery. So this is a combination series and parallel circuit. We're not going to get any more crazy than this, so it's not going to be too bad. I mean, I guess we will do this one later, but nothing really bad with series parallel going in anything like that. So A wants us to find the total resistance of the circuit. So whenever we're doing this, we kind of want to combine like resistors. So what do we have two of? Do we have two resistors in series or two resistors in parallel? Yeah, we have the two in parallel. So let's start with those to get our total resistance of the circuit. So we're going to start by trying to get rid of that parallel resistor. So I have these two 10 ohm resistors in parallel. 10 ohms in parallel. So we're going to combine these. So again, when we add resistances in parallel, it's 1 over that total resistance, or 1 over equivalent resistance is the other word you might hear, equivalent. So 1 over that total resistance is going to be 1 over 10 ohms plus 1 over 10 ohms. Well, 1/10 plus 1/10 is 2/10, which is 1/5. All right, and we need to invert our fraction, right? 1 over total resistance is 1 over 5 ohms. 1 or 2 people didn't do this last step on the homework. We need to invert our fractions in order to get just total resistance. So total resistance for that parallel path is exactly 5 ohms. So that's the total resistance for this small parallel path. So I can kind of redraw my circuit here where I still have a 6-volt battery. going through this 20 ohm light bulb. But now this path here has an equivalent resistance of 5 ohms. So it's almost like I just have a single 5 ohm resistor there. So instead of drawing this parallel path with two 10 ohm resistors, I just draw a resistor with 5 ohms. And again, we see here, parallel, we have smaller resistances because I can go through here or here. So it makes it easier to get through that path, and I have a resistance smaller than my individual resistors. But now what type of circuit do we have here? Yeah, now we have a simple series circuit. And so when we have a series circuit, our total resistance, we just add these all up. So total resistance, just 20 ohms plus 5 ohms. So my total resistance for the entire circuit is 25 ohms. So in parallel, we see smaller resistances because I can go through here or here, so it's easier to get through this path. So I get a resistance smaller than the individual resistors. But in series, I have to go through here and here, so I end up with a bigger resistance. My resistance is bigger than my biggest resistor, which is 20 ohms. All right, so when we do this, we have to split these up into individual sections. So it's going to be easier to do this part by part, simplify whatever resistors you have two of. If I have two resistors in series, add those up first. If I have two in parallel, combine those first, and then slowly collapse down our circuit like this. We'll do 3 next class where we do that a little bit more in depth. And we could have done this all at once. If you're kind of lazy like me, we could have seen series resistor. You just add that, right? So it'd be 20 plus. Well, and then we have to add these two in parallel. So it'd be 10 inverse plus 10 inverse, and then we have to inverse that. So if you wanted to do this all at once, you could have done something like that. Inverse of 10 plus inverse of 10 inverted, and then plus the 20 in series. So if you're a lot quicker at this and you're good at getting these correct, that's a faster way of doing it. If you're getting these wrong, then please go through all the little steps. So B wants us to find our total current for the circuit, or sometimes it might say how much current goes through the battery. So that's just Ohm's law. Total voltage equals total current times total resistance. Total current, just divide resistance over is total voltage divided by total resistance. We have a 6-volt battery with a total resistance of 25 ohms. Quick way of solving this would just be multiplying the numerator and denominator by 4. So we have 24 volts per 100 ohms. Or we have a total current of 0.24 amps. So these are kind of the easier parts. Finding for the total circuit is going to be a little bit easier than what we're going to do when we're solving for each of the individual resistors. All right, C is talking about how much charge flows through the circuit every 10 seconds. So this is the total charge through the circuit. Well, charge, Q, is related to the current. Well, it says per time. So current is just the amount of charge flowing past a point in a given amount of time. And I think y'all did calculus in pre-cal, right? Y'all have done some derivatives in pre-cal. Anytime you see a delta, you should be thinking, hey, that's kind of like a derivative. Delta Q is dq, so dq dt, or the derivative of charge with respect to time. Just kind of a thing you can think about. Did y'all not do derivatives in pre-cal? I thought y'all did simple derivatives in pre-cal. I think y'all did. I heard people talking about derivatives who I know weren't in calculus. Yeah, I mean, you could do this with a simple power rule, like if your charge was expression, say your charge was x squared or some expression like that. But yeah, I mean, it's just delta you could replace with d, derivative of q with respect to time, instead of dy dx, dq dt, something like that. Well, we're trying to find amount of charge, so multiply time over. So current times time equals the amount of charge flowing past that point. And I don't think, did y'all do integrals? You could like multiply over and integrate both sides and do a little differential equation. But I don't think y'all talked about integrals or antiderivatives yet. All right, so current, we have 0.24 amps going through this. And we're trying to figure out every 10 seconds. 0.24 times 10 is just going to be 2.4 coulombs. I mean, I'm obviously not going to ask you a derivative question like that. That would be something that you would run into Physics C, which I have had people go from dual credit to Physics C and be really successful. Yeah, two of my students from last year in dual credit went to Physics C, and one of them got a 4 and one of them got a 5 on the AP test. So yeah, and the one who got a 5 taught themselves rotational motion. The one that got a 4 just never taught themselves rotational motion, and they just went off everything they learned from dual credit. So just taking the dual credit class and not studying, if you're good enough at dual credit physics and you know what you're talking about, you can easily get a 3 or a 4. Free body diagrams. Yeah, free body diagrams are good. I mean, I feel like a little bit of a hypocrite every time I tell you to draw a free body diagram. I never drew free body diagrams, but I got the problems correct. So yeah, I'm trying to, like, whenever I went through physics, I like never drew a free body diagram, like, ever. But the difference is I got the math correct and I got the physics problem correct. So that's the difference. Yeah, kinematics and forces. So I also put the other thing, if you're trying to prepare for the AP physics test, is there's some of those ranking tasks where it's like rank these in order. Those are also really good ones, and some of them went through kinematics and forces. So yeah, just look through those. I have the videos. You don't have to do them as rigorous as I'm having the AP students do them. But yeah, you can go through and they're relatively fast, just like 1 or 2 AP test questions in the past and just 3 different. See, the funny thing about kinematics is so many people at the beginning of the year are like, does it get easier than kinematics? And they don't like kinematics. But that slopes and areas are all part of kinematics, though. All right, what gets more current? The light bulb or one of the resistors? So current is moving electrons, right? So this is all conservation of charge. These electrons aren't getting created or destroyed in these really low power circuits. So I send out a few electrons. These electrons aren't getting created or destroyed, so I have 0.24 amps going through here. How much of that 0.24 amps goes to the light bulb? A little or all of it? It's not a little, it's all of that current. All 0.24 amps go through it, right? Because current is charge, right? Current is charge. Charge is not created or destroyed. And again, we need really high energy things to create or destroy charges. And again, even atomic bombs, like when you're talking about modern physics, atomic bombs are actually still relatively low energy reactions, which is kind of scary what a high energy reaction is. So even atomic bombs don't really create or destroy much charge, maybe a little bit. But yeah, we're talking like black holes, massive stars. Yeah, so all the charge, electrons aren't being created or destroyed, so all the electrons have to go through here. But then they get here, and they have to make a choice. Some of those electrons are going up here, and some of those electrons are going down here. Let's say current 1, current 2. So we're going to see that current is going to split up. Some electrons go up, some electrons go down. So here we'll see our total current is going to be the combination of these plus 1, 2. So in parallel, we see that current gets split. So some goes up, some goes down, and they're identical resistors. So if they're identical resistors, how much is each one going to get of the current? Yeah, they're each going to get half. So they would each get 0.12 amps. But then we get here, and then everything combines back together, and we end up with a full 0.24 amps again. So 0.12 amps up, 0.12 amps down. So parallel, the current gets split, but in series, they get the full current. And again, you can imagine current as like the people walking through the grocery store. So this is like the grocery store has a single entrance. Every single person has to walk through the entrance. They go through the store, but then they get to a point where there's two checkout lines. Some people go to one line, some people go to the other line, so the people split up to go through the lines. But then they come back together to go through that single entrance out of the store. So every single person leaves the store again. You don't have people just disappearing randomly in the store. Hopefully you don't. All right, so E. E wants us to get the voltage drop across the light bulb. And this is, I think this is about how I set up your test, where you're kind of going through things in a order where I'm kind of structuring it for you, where you're not having to really go through. So how I've kind of split this up is how you would kind of go through this. I never actually answered D, did I? Which gets the most current? Light bulb. Light bulb gets more current than each resistor. Both resistors get the same current as the light bulb, but each resistor gets less. They each get half. All right, so here we want just the voltage drop across the light bulb. So voltage drop across the light bulb, let's call that L, is equal to current across the light bulb times resistance of the light bulb. So the voltage drop across the light bulb, that light bulb gets all 0.24 amps of current, but it only has a resistance of 20 ohms. Well, 0.24 times 2 is 0.48. Times 10 is 4.8. So the voltage drop across the light bulb is 4.8 volts. Now, kind of just a little thing I noticed, it's not the biggest deal in the world, but here it asks for voltage drop. So it drops by 4.8 volts. So the voltage drop, I would write a positive voltage drop, right? Because I had a voltage drop of 4.8 volts implies that it just drops by 4.8 volts. So if you write a negative voltage drop, that kind of implies voltage goes up. If it just asks what's the change in voltage, I could say change in voltage is negative 4.8 volts, but the voltage drop is positive. It's kind of a language thing. So I corrected this on a few people's paper because it asked for a voltage drop, but that's not the biggest mistake in the world. So if it asks voltage drop and it's losing voltage, you would call it a positive. So F, this is where we have to think a little bit. F wants us to get the voltage drop across each resistor. So I'm going to draw this circuit again. And this might be helpful to keep drawing out the circuit or drawing it really large where you could write all of these on there. But there's a lot of small things to keep track of here that it might be best if you just draw these out. It might be really helpful to kind of figure out what's going on. So now we get to voltages. So I go across my battery and we add 6 volts here. So that means I have 6 volts up here. And how much voltage do I have when I return to my battery? When I return to my battery, I have how many volts? 0, right? Yeah, 0. So we have 0 volts by the time we get back to our battery. We've used this all up. And it's not that there's like this magical 0 we return to. It's just that the 0 is kind of defined as the lowest potential in the circuit, just like I might call the top of this desk 0 height. It's just, I call this 0. It doesn't necessarily have to be 0. You could say return to 2 every time. It goes, say, 2 to 8, 2 to 8, 2 to 8. It just returns to the same minimum value here, and it makes the most sense to call that minimum value 0. So a little caveat if you ever do electrical engineering or something. All right, we go across the light bulb. Well, that light bulb takes 4.8 volts. It has a voltage drop of 4.8 volts, so it has a change in voltage of negative 4.8 volts, which means that I started with 6, I lost 4.8 volts, so I have 1.2 volts here. We're assuming perfect wires. If we have perfect wires, it doesn't take up any of this voltage. So I still have 1.2 volts down here. Yeah, we subtract that 4.8, so 6 minus 4.8 to 1.2. So I have 1.2 volts across this resistor and 1.2 volts across that resistor. So how much voltage does each resistor get? Does the voltage split? I go from 1.2 to 0, 1.2 to 0. Yeah, in parallel, they both get this full 1.2 volt drop. So the voltage drop across each resistor, so again, voltage, or I guess I could write this as voltage drop for each resistor, is equal to 1.2 volts. They both get that entire 1.2 volts left over for them. So that's where we get to this. So in series, so that light bulb is the one in series. And then we can think of the light bulb as being in series with both these resistors, kind of like how we set it up here, how the light bulb is in series with the total of those two resistors. So in series, they're splitting the voltage. This gets 4.8 volts, the light bulb gets 4.8 volts. These get the leftover 1.2 volts. So in series, these are going to split the voltage. But in parallel, they get that full voltage, which is a little bit different. They're not getting that entire 6 volts from the battery, but they have 1.2 volts left over, and they're both getting that full leftover voltage. So they both get that entire 1.2 volts. So it's because the voltage drop, well, I went from 1.2 to 0 across here. I went from 1.2 to 0 across here. So again, these are those 4 rules that we talked about before that are more important than ever for these series parallel circuits. All right, so these are pretty much all the things I can ask for on here. I could ask for, actually I didn't ask for current. Do I ever ask for that current? I didn't, but let's do that. Let's get the F2. Let's get the current through each resistor. So current through each resistor. So current is going to be, so voltage equals current times resistance. So current is going to be voltage divided by resistance. And we're looking at the individual resistors. Well, that gets 1.2 volts. And they each have a resistance of 10 ohms. So 1.2 divided by 10, you would get 0.12 amps. So each resistor is going to get 0.12 amps, which matches our prediction up here, right? So they each get half. So I had 0.24 amps. When those get here, half goes up, half goes down. They each get 0.12 amps. That's the other thing I could ask you for on here. So this light bulb got the entire voltage through the circuit, or the entire current through the circuit, and these two had to share the current. Then this light bulb was in series with this, so they all had to share the voltage. The light bulb got part of the 6 volts. These got the rest of the 6 volts, but they both got the full voltage. Quite a bit going on there. So make sure you're asking questions if you're unsure about any of these values. Now we get to G. G, if the light bulb is removed from the circuit, how much current does each resistor receive? And notice a light bulb removed and not replaced with wire. Yeah, so what ends up happening here is if I don't replace this with a wire, we get an open circuit. And in an open circuit, there's no current. So we open this up and there's no current. So it's just like this light bulb here. If I plug it in, I have to plug in both sides in order for any current to flow. But the second I just have one side connected, just no current flows. So I need to have that entire path. And by the way, this is all just due to the fact that electrons repel each other. So all the electrons want to be equally far apart. So this battery is pushing on the electrons. It's just the electrons get to here and then they're stuck at this point, and it creates a backup, and they're all repelling and they start pushing back this way. So we kind of have electron forces. The ones that are stuck over here and the battery pushing, they kind of push on each other and cancel out, and so the electrons just end up sitting here. But whenever I put this here, now all of a sudden I have a place for the electrons to go. So the electrons get pushed this way, and they're pushed and they're allowed to return, and then they get pushed out again. So I need that for the entire circuit. Otherwise, those electrons have nowhere to go. They get pushed over here, and then they push back, and then all current just stops. I could ask the question where I took this out and replaced it with a wire, and that would be a different question, because now if I took this out and it only had a wire there, then it would be a parallel circuit, and then I could have some interesting things going on there. If I were to replace this with just a wire instead of the light bulb, then it would be parallel, and then I would see that these would get more current as they get all 6 volts, and as they got all 6 volts, they would end up with more current. Look at H. Try to think of what H is going to do. I want to see your opinions on that. If I remove one of the resistors, how much current will each component receive? Do you think the current will go up or down for each of these? I will say one will go up and one will go down. So which do you think is going to get more current and which do you think is going to get less current? So we still have this light bulb here. But now I remove one of the resistors. Which one of these do you think is going to end up getting more current, the light bulb or the resistor? Yeah, now it's just a regular series. So before the resistor was sharing current, and when it was sharing current, each one got less. But now all the current goes through here. So this is probably going to get a bigger current. But I made this instead of parallel, I turned it into series. Which has more resistance, parallel or series circuits? So series circuits have more resistance, so I expect my current to go down. So even though this gets more current because it all has to go through here, overall I expect my total resistance to be bigger, and because I have a bigger total resistance, it means the light bulb is going to get less current. So let's kind of see that in action. We're going to have to get another total resistance. Well, these are in series, so I can just add them, right? So I have a 20 ohm resistor plus a 10 ohm resistor. I just have a 20 ohm and a 10 ohm exactly in series. So my total resistance is now 30 ohms. So voltage equals current times resistance, or total current is total voltage divided by total resistance. We have a total voltage of 6 volts divided by 30 ohms. Well, 6 divided by 3 is 2 divided by 10. Well, 2 divided by 10 is 0.2 amps. Now, these are in series. In series, each resistor gets the full current, right? So the current through the bulb is equal to the current through the resistor is equal to my total current is equal to 0.2 amps. So I removed a resistor in parallel, so it made the resistance goes up, so my total current went down. Yeah, that's mathematically why the total goes up, because you're to the not to the negative. Yeah, to the negative first power. Yeah, you can write it that way. So yeah, that's why, because we're adding these as reciprocals. Or we can imagine you close a checkout line in the store. So instead, so everyone has to go through here and they could split here, and it made it a little bit easier to go through the store. But now everyone has to go through this, and they're all forced to go through both of these, and it makes it harder to go through the circuit. So our total current went down a little bit, 0.24 down to 0.2 amps. And then we see kind of our prediction here. The bulb before was getting all 0.24 amps, but now it's only getting 0.2 amps. So that light bulb is getting less current. But the resistor, that resistor was only getting 0.12 amps. Now it's getting the full current, which went up to 0.2 amps. So we saw the bulb ends up with less current and the resistor ends up getting more of the current. All right. So far, so good. If you have questions, you can ask them now, or if you kind of look through this again and you're trying to work on the homework and you still have questions, you can ask them next class also. All right, so let's do 2, and then we'll end here. So 2, we have a circuit with 2 light bulbs. connected to a 1.5 volt battery. So that's just like a normal AAA or AA battery. Those are all 1.5 volts. At first, both bulbs glow. Bulb 1 has a 10 ohm resistance. Bulb 2 has a 15 ohm resistance. So we want to find the total resistance of the circuit. So looking at this circuit S, that's a switch. The switch is open. Yeah, the light bulb from the previous one, the light bulb got less current and the resistor got more current. But they both end up with the same. Both the light bulb and resistor get that 0.2 amps. So we have a 1.5 volt battery. We go through this light bulb. Bulb 1 is 10 ohms resistance. Bulb 2 is 15 ohm resistance. We go down here. Now, we have this path here that has a switch. This switch is open. So does that affect the circuit at all? Yeah, we'll get to the switch in a second. But that switch is open right now. So is that doing anything to the circuit? Well, it's open. So the switch is open, which means no current, which means we can ignore it for now. So for now, I'm going to ignore that switch. That's not part of the circuit. So we can almost just erase that from our circuit for now. So let's erase it from the circuit and just say it's not there. Well, that switch is open. It doesn't affect the circuit. So we pretty much just have a circuit like this for now. I mean, we'll see later. That'll be part E when we close the switch. So what type of circuit is it with the switch open? Yeah, we just have a series circuit with this open. So series, our total resistance is just going to be the sum of the two. 10 plus 15. So we get a total resistance of 25 ohms. B, total current, just like what we've been doing. Total voltage equals total current times total resistance. Total current is total voltage divided by total resistance. A 1.5 volt battery, 25 ohms of total resistance. Actually, I don't even need, again, 25 makes this real easy. Multiply the top by 4. 1.5 times 2 is 3, times 2 is 6. So we get 6 divided by 100. So we get a total current of 0.06 amps. So this has just been like the last class. C wants us to get the voltage drop across resistor. Before we get voltage drop, how much current does each of these get? Do they have to split up the current, or do they each get the full current? So they each get that full current, right? In series, all 0.6 amps goes into each resistor. So 0.06 amps. 0.06 amps, we only have one path. So at all points on that path, every person has to go through that store. Every electron has to go through every light bulb. So every light bulb gets 0.06 amps of current. So the current through bulb 1 equals the current through bulb 2 equals our total current equals 0.06 amps. And so because of that, we can get our voltage drop, voltage through 1. We should really do change in voltage across 1 is current 1 times resistance 1. So 0.06 amps with a 10 ohm resistor. So the voltage drop across 1 is going to be 0.6 volts. Again, because I'm solving for voltage drop, I'm calling it positive because I subtract a positive number, right? And then the voltage drop across 2, that also gets 0.06 amps, but it has a 15 ohm resistor. 6 divided by 2 is 3, 6 plus 3 is 9, 9 times 0.09 times 10 is 0.9. So the voltage drop across resistor 2 is 0.9 volts, or just put it in your calculator. And we see this works out just fine, right? Because I have 1.5 volts here. I lose this one, I lose 0.6 volts. So I go down to 0.9 volts here, and then I lose 0.9 volts, and then I go down to 0 volts here. So I've used up all my voltage by the time I get back to the battery. And again, we see series, each resistor got the full current, but they had to split up the 1.5 volts. So this got 0.6 of the volts, this got 0.9 of the volts. So which bulb is going to be brighter here? 1 or 2? Same current, but 2 got more voltage. So 2 is going to be brighter. It has more power. And that's what D is asking. We can actually prove that here. How much power does each light bulb receive? Well, we can just use our power equals current times voltage. We've already solved for both of these. So resistor 1, 0.06 amps. And that takes up 0.6 volts. 6 times 6 is 36. Power across 1 should be 0.036 watts, right? I got my decimals right, correct? Yeah, 0.036. And then the power across 2 is the current across resistor 2 times the voltage drop across resistor 2. So 0.06 amps, but this one takes up 0.9 volts. Uh, 9 times 6 is what, 54? Wait. Yeah, 54. I don't know why I was blanking on that. 54, so 0.054 watts. So which one is brighter? Yeah, 2. 2 is brighter because it has more power. Right? Power is the amount of energy used per time. So more energy, more power. Again, this is assuming identical light bulbs that behave in the same way. Obviously, there's different types of light bulbs. Like I've talked about before, we have incandescent light bulbs, which are the ones like this that get hot and glow. Those are less efficient than, say, an LED. So it'd have to be 2 similar types of light bulbs that receive different powers, glow different brightnesses. So yeah, we're assuming they're the same type of light bulb. There's obviously a little bit more that goes to there. And then we close the switch. Yeah. So now we close that switch. Now it's causing a closed circuit. So let's redraw this again. 1.5 volts. We have our 10 ohm light bulb. we have our 15 ohm light bulb. Go through here. Now we close the switch. When we close the switch, is that going to affect our circuit? Does that switch provide a full current path back to the battery? Yeah, there's a full current path, right? So current can go through here, or current can go through here. So there is a full current path here. Now, how much resistance do wires have? So they're pretty small. In general, they're really small. The wires I have here that I'm using, they're like less than an ohm of resistance, somewhere between like point. It's not that small, like 0.2 to 0.7 or somewhere around there. But we're going to be assuming perfect wires, so we're going to say this is a 0 ohm path. In reality, you can never have a 0 ohm path. It's just not possible unless you have superconductors. They're 0 ohms, but they have other things causing resistances in there. So 0 ohms. All right. What does 0 ohms look like in a grocery store? No resistance to leaving the store. Hopefully not you. So we have a choice. We just walk out of the store without paying, or we go and we pay. If there's no consequences, which are you going to do? Pay and wait in line, or not pay and walk out of the store? Well, pre-orders. I guess that's the better way of doing this, is you can pre-order and you just like walk in, pick it up, and leave. I guess that's the non-illegal way of doing this. But which path are you going to take? If there's no consequences, I think everyone's always going to go through the one where you just walk out of the store. So when choosing between something with resistance and no resistance, all of that current will choose the path with no resistance. Choose the path with no resistance. So this is what's called a short circuit. In general, short circuits are really bad. Short circuits are something with a really low resistance. And again, we have power equals current times voltage. And we see with the low resistance, as resistance goes down, we see that current goes up. So if you have a really low resistance, you have a really high current. If you have a really high current, you have a really high power. Power is the amount of energy used. And because a lot of energy goes into, say, heat, just imagine how hot your computer gets, why you need fans on it, because there's so much electronics packed densely in there. So if you have a lot of power, you have a lot of heat, you have a lot of hot stuff, and you can start fires this way. So this is how short circuits can cause fires and why you don't want to mess with them. That's why that whole, what is it, that stupid penny challenge that people are doing, where they like have a penny across and then they plug it in, like they have it across the two metal things and they plug it into the wall and it like explodes. That's what's happening there. You have a short circuit where it sees a path with very low resistance. The current all takes that path. A lot of current can flow through it. So you have a lot of power, you have a lot of energy, and it gets really hot and you can catch things on fire. Yeah, don't do that. This is why short circuits are really bad. And so yeah, all of my current is going to choose this path. And I can kind of see this. Let's look at just this side over here. If I'm trying to find what my total resistance is over here, well, that's parallel, correct? Resistance total will in parallel 1 over. So it's equal to 1 over 15 plus 1 over 0. All right, so 1 over 0 is pretty much infinity. So we get is equal to infinity. Now, obviously, there's limits here, so you would have to do limits as things approach these values, but we're just going to say that's infinity. Infinity plus anything is infinity. Then I do the flip, so resistance total, 1 over infinity. So we get pretty much 0 resistance. So that path just ends up with no resistance and everything goes through there. So everything goes here. So what happens to that 15 ohm light bulb? No resistance, all the current goes through here. So what happens to the 15 ohm light bulb? Yeah, no current and it turns off. Now, there's no current. It's almost like this light bulb doesn't exist. Now what happens to the 10 ohm light bulb? The 10 ohm bulb still has a non-short path back to the battery. I removed this 15 ohm resistor. So it's pretty much like that doesn't exist in my circuit anymore. So if I have one less resistor in parallel, my total resistance is going to go down, which means my total current is going to go up. The 10 ohm resistor, now it's not having to share voltage here anymore, right? This is pretty much not there. That 10 ohm resistor gets all 1.5 volts, so that means the voltage goes up. Current goes up, voltage goes up. That means the power equals current times voltage. Power is also going to go up. So that 10 ohm bulb is going to get brighter, more brighter. That 10 ohm bulb gets more brighter. And we can actually test this. So we have these two light bulbs here. And these are actually really close to those values. This is a 1.5 volt battery. Get in there, you stupid wire. These wires are all bent. Which one of you is not connected? Oh, there they go. So here we see, you probably can't see it very well, but this one is barely lit up and this one is also just glowing the tiniest amount. Now, if I just take a wire, if I can grab one. So I just take a wire, and now instead of having the current, say, go from here through here, let's just attach this wire here. So I'll short it out. So I'll touch this one to this side, and then I'll touch this one over here. We see this one is completely off, and then this one got brighter because now it's not having to share. Or I could do the other one. Now let's short out this light bulb. So we can see that one is lit up, but the second I give a path that's just wire, everything wants to go through the wire, and then this one gets brighter. I disconnect it, it gets dimmer again, connect it. So if we have an option, our electricity is always going to shoplift if given the option. So we see it get brighter when it no longer has to share. and then goes back where these are both really dim. And then again, don't mess around with short circuits. Here, I was only shorting out one of the light bulbs, so it's not so bad. You don't want to intentionally create a short circuit. Again, if you were to do that with, say, a battery, where I would connect this directly across the battery and I just left it there for a long time, the battery's going to get really hot. The battery's probably not going to like explode in a big explosion, but it can definitely like burst open and cause problems. But yeah. All right, so that's pretty much it. Whenever we short out the circuit by closing the switch, the light bulb turns on, but the other one is all of a sudden getting more current. Yeah, so you can actually use that to start a fire. There's people who do it if you have like a 9-volt battery and still wool. You like take the still wool and you put it up to the 9-volt battery, and it actually shorts out the battery, sends a high current through it, and can ignite the steel wool. Obviously, don't do this at home or unattended. Oh, you did that in chemistry. But yeah, you can use that to start a fire. You're pretty much shorting out the battery, sending a really high current, which makes the power go up, makes it get really hot. When that steel wool gets hot, it can actually combust. Yeah, metals are surprisingly combustible. It's the whole oxidation thing, which is burning. But yeah, see you, Vincent. But other than that, yeah, this is all we're going through in class today. I'll go through number 3 to not next tomorrow, but Thursday. Keep showing up, work on this, try to do some of the classwork and the homework once you do this. And then if you still haven't taken your tests, please do that and kind of catch up. We will have our test next week, and I'll put out a review for that soon. But other than that, have a good day.